All right, here we go. All right, so we're going to repeat this exercise for x equals t squared plus 2t. So we got a couple of parametric equations, and we're going to find the points determined by these variables. Okay, that's easy. I don't even think we need to do that, do we, guys? You know how to do that, right? You know, if you pick a t-value, you're going to get ordered pairs, right? Okay, so that part I think you got. B says eliminate the parameter. In other words, find an algebraic relationship between x and y. So take your two equations and get rid of the parameter. Well, how did we do this yesterday?
So we, on x, we got t by itself.
And we did, that's what we did yesterday. I think this time it would be easier to get t by itself here, wouldn't it?
Yeah.
For y?
And then plug that in.
Yeah. So I'm going to say t equals y minus 1. And then x equals y minus 1 squared plus 2 times y minus 1, which I can simplify to like terms. So I got y squared minus 1.
So in these, well, the variable that's attached to the y that's the square root always cancel.
No.
Because it canceled yesterday.
Because they were the same two equations.
Okay.
Just switched.
Okay.
It has to do with that's a TT.
Okay.
That was free to make them cancel.
Okay.
Okay, now, this is the direct algebraic relationship between x and y. In other words, it's an equation that has x's and y's. Now, we know that a squared equation is a parabola. When y is squared, it's a sideways parabola. This is not a function, right? We can graph it parametrically, though, on our calculator. Let's refresh our memories how to do that. We're going to graph it on our calculator now. Certainly, having taught or figured out these points, we could plot them by hand. But since I don't have them, I'm going to go ahead and just graph these equations parametrically. So I've used my calculator since yesterday, so I'm going to go back into mode. Go over to parametric, make sure you're in parametric mode. And then y equals, or I press y equals, but then it asks me for x, so that's t squared plus 2t. And then y is t plus 1. Everybody remember how to do that from yesterday? Now, I have no idea how my window's set, so I'm going to take a quick look at it. Do you remember what we talked about yesterday?
It's like something square. Like you have to square your window or something.
No, I mean you can, but your step, you need to keep an eye on your step, because however big your step is, you need to make sure you're getting a nice smooth curve. If you make your step too big, it is jaggedy. So you want to, I'm going to set my step at 0.1 and just see what happens. And I'm setting everything at -10 to 10 just to start. Yep.
So the equation doesn't have to be a y equals?
Not if you're putting it in parametric form.
Okay.
Parametric form, you're putting in x equals and y equals.
But
If you're in
if you're
function mode,
eliminating the
it has to be.
parameter.
What?
I mean, it's like eliminating the parameter. When you eliminate the parameter and you find the algebraic relationship, it doesn't have to be a y equals statement?
No.
Okay, got it.
Okay, did you get a sideways parabola?
Yes.
Just like that? The transformations that we've been talking about apply here too, but they're a little bit wobble-jawed. Y squared equals x plus 1. Does it make sense to you that this thing would be shifted 1 unit to the left? Okay. All right, so so that's that. What else was I supposed to do? Oh, that's it, we got it. So you need to be able to take parametric equations and remove the parameter. And then it's a good idea to be able to graph parametric equations on your calculator. Easy. All right, now number 3. Number 3 now talks about inverses. Look what I found in the trash. Someone threw this away. Alright, so we're going to look at inverses. So consider the absolute value function. Everybody knows what that looks like, right? Y equals root x, absolute value x. And if I actually plotted some points here, you know it's a V. But if I plotted some points, this would be 1, 1, 2, 2, negative 1, 1, negative 2, 2. Everybody okay with those points? And then connected on, there's your nice little V. Now, inverses switch the x's and y's. So what was an x becomes a y, and vice versa. So if I were going to graph the inverse of this, I would take each of these ordered pairs and switch their x's and y's. So this point would become 2, negative 2. I'm not changing the signs, it kind of looks that way here. I am flip-flopping the ordered pair. So it's 2, negative 2. And then 1, negative 1. 0 doesn't change. And actually, these don't change either, do they? Well, look what happens. The inverse is still a V, so it's still the same shape. Is it a function? No, it is not a function. Not a function. Now, I want you to go back and think about something we talked about before. What did we say 1 to 1 meant?
For every x value, it has only one y value.
Right, and how could we see that graphically? The horizontal line test, right? And the vertical line test had to pass both. So if you're going to be 1 to 1, you have to pass both. Now, clearly, guys, is this thing a function? Yes. It is not 1 to 1, though, because it doesn't pass the horizontal line test. And the fact that it doesn't pass the horizontal line test means that there are repeated y's, which when I flip-flop those to do the inverse, those then become repeated x's. So if we want to know if something's inverse is a function, we don't really have to go through all this trouble. If its inverse is a function, it will pass the horizontal line test.
So the original.
If the original passes the horizontal line test, then its inverse is a function. Because again, remember, the horizontal line test checks for repeated y's. See how these y's are repeated? When you do the inverse, those y's become x's. So now what were repeated y's have now become repeated x's. So if you don't pass the horizontal line test, then your inverse is not a function. All right, number 3, think about the reciprocal function. Does the reciprocal function pass the horizontal line test? Yes. Therefore, is its inverse a function? Yes, because it passes the horizontal line test. In other words, the reciprocal function has no repeated y's.
When you do when you do the inverse, is it a reflection about the order?
It is a reflection across the identity line.
Okay.
It's a reflection across this line right here. And that makes sense, because what's the equation of this line, the identity line? Y equals X, and when I do an inverse, what do? Switch to X equals Y, right?
Since you said it's reflecting over the identity line, those asymptotes just be the same inverse?
Yep. There's the identity line. If I reflect the reciprocal function across that, if I fold it across that, won't I get the same curve? There are many functions who are their own inverses, and this is an example of one. The reciprocal function is its own inverse. It is 1 to 1. It passes both tests. Okay, so we just hit on a couple of kind of accidentally really big ideas. One is that the inverses are a reflection across the identity line. So depending on how good a drawer you are, any shape, you could find the inverse by just reflecting it across that line. We also find an inverse by flip-flopping the ordered pairs. That's easy. If you know your dots, just flip-flop them, and that's your inverse.
I kind of have two questions about the identity line.
Mm-hmm.
Would you consider something symmetrical across the identity line if it is the identity line? Okay, and then obviously, would it also just be flipped and be the same thing if it was the inverse of the identity line? Would it still be the identity line?
Yep.
Okay.
Yep, it's its own inverse. All right, now we're gonna find some inverses. These guys are not their own inverses. So we talked a minute ago, if we have the picture, we can find the inverse by folding it across the identity, or by flip-flopping the ordered pairs. How do we find the inverse, though, if we have an equation? So, Sir is remembering the process. He says, okay, I'm gonna think of this as Y. Now, what do inverses do? They exchange Y and X. What was an X becomes a Y. So the inverse equation, this is the original. The inverse equation will be X equals 3Y minus 1. So X plus 1 equals 3Y, and Y equals X plus 1 over 3. That is the inverse, and we will use inverse notation, which is F inverse, and it's X plus 1 over 3. Now, kids, this is absolutely fine, and sometimes this is how we have to do it because the problem is so complicated, but you could figure out the inverse for this problem pretty easily. Remember, the inverse undoes whatever the original did, okay? So, for example, if I start with the number 6, I'm just making it up, start with the number 6, and I put it into the original function, it would give me a 17. Would you agree with that? Now, if I take that 17 and put it into my inverse, what does it give me? The 6 back again. That's what inverses do. The original ordered pair was 6, 17. The inverse ordered pair is 17, 6. Inverses undo each other. So, think about this function. When you give it a number, like 6, the first thing it does is multiply by 3 and then subtract 1. So undo that, put it in reverse. Think of it as a machine. Add 1, divide by 3. That's exactly what the inverse is going to do. It's going to undo the operations. Okay? Of course it makes sense. Math always makes sense. All right, now some of them are not that easy though. This one is a little bit harder because the function is not just a boom, 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 boom. This one you would have to do the numerator and do the denominator, right? Separately. So how do we find the inverse here? Well, we're going to go through Sir's steps. It's a little more complicated. There's more of it. But here we go. So X equals 4y plus 1 over y minus 2. Everybody okay with that? That's the big switch. That's the key to the problem right there. Now we gotta get y by itself so that we can answer in inverse notation. So what do you think? How are we gonna get y by itself in that guy? What's your idea?
Can we take the entire y minus 2 and multiply that?
Oh, sure, we can bring this over to here. Absolutely. So xy minus 2x. So we're gonna multiply this over to here. In other words, get rid of that fraction.
Yeah.
Perfect. All right, now what?
Add the 1,
Do what now? Add the 1 and divide by, or subtract the 1 and divide by 4?
Oh, yeah.
Now, let's look at that
Something
for a
like
minute.
that xy.
Because that does what we need to do. We need to get y by itself, but what's the problem with that?
This is by itself.
Yeah, we still got a y over here, right? So we can't do that. I mean, we can do that, but it's not right.
So then,
What do you think? Mr. Whalen?
Leave the y's on one side and distribute.
Exactly. We need to get all the y's on one side, and it does not matter which side. So I'm gonna go ahead and bring this y over here and move the 2x over here. We gotta get all the y's on the same side of the equation, either side, doesn't matter. Then, like he said, what can I do over here? He said distribute, it's factoring, right? Same thing, we're gonna factor out a y. And then we can divide by that parentheses. So our inverse is gonna be 2x plus 1 over x minus 4.
so we can't do what we do over here, what we put with that.
I mean, not you can't intuitively figure that out. There's definitely some patterns, if you look at the original problem, and what we end up with, there's some relationships there, but, you can't just undo it backwards.
And what, like, I noticed that 4x is half, and then, the extra,
I don't know, you can notice all that kind of junk you want, I'm just gonna do the problem. By the time I notice all those weird things, I could have the problem done, so I'm just gonna do it. Now, we're gonna talk about something real quick here. What is the domain of the original function? The domain of the original function.
Negative infinity to 2, not included, and then 2 to infinity.
Okay, now for those of you that are thinking, what, stop and think. What do we know about denominators? They can never be 0. So x cannot be 2. Right?
Right.
Totally good with that. All right, tell me about the range of this original. Now, if it helps you, think about horizontal asymptotes. Does this guy have a horizontal asymptote? He does. Where is it? 4. So if there's a horizontal asymptote running through my picture of 4, then y can't be 4, right? So what's my range?
From negative infinity to 4 not included, negative 4 to positive infinity.
Exactly. Now, those are the domain and range of the original. Now, let's look at the inverse. Tell me what the domain of the inverse is.
Negative infinity to 4, union 4 to negative infinity, positive infinity.
And how about, look at this horizontal asymptote. What's your range?
Negative infinity to 2, union 2 to positive infinity.
Oh my gosh, kids, what happened? The domain of the original is the range of the inverse. Does that make sense? Yes, because when we find an inverse, we flip the ordered pairs.
Wouldn't that range also not be able to equal 0? Or I guess x can equal 0, so.
Well, x can equal negative 1/4,
Okay.
and that would give you a y value of 0.
Okay.
So, one more time. The the domain of the original is the range of the inverse. And the range of the original is the domain of the inverse. Right? Sometimes range can be a little tricky to find, especially if you don't have a graph. So one way to find range, always, is to find the domain of the inverse. It's almost always easier to find domain than it is to find range. So if you are confused about the range of something, find its inverse, and whatever the domain is of the inverse is going to be the range of your original. All right, couple more. Gotta find a couple more inverses here. You have the next one done. It's the square root of x minus 3. Right? So, let's see, how am I going to get y along here? I'm going to have to square both sides.
Oh, I'm dumb. Why don't I do that?
So the inverse is x squared plus 3. Okay, we have a problem. We need to talk about this for a minute. What does that original picture look like? You should know that.
A half parabola.
It is the square root function moved 3 units to the right. So isn't that a picture of this? Right, now tell me what this looks like. You should know what that looks like. The inverse
It'll be a
is,
parabola along the line.
isn't it this? Okay, now remember, to get an inverse, you take the ordered pairs of the original and switch them. There is no way that that shape will give you this shape. There's too much of this. Would you agree?
Yeah.
Why is there too much of this? Because the domain of this guy right here is what? What is the domain of the original function? 3 to infinity. Can't be less than 3. That means that okay, wait. What's the range of the original? What's the range of the original function? 0 to infinity. That means that your inverse, and you have to make a notation of this, guys, your inverse has a domain of what? 0 to infinity. Even though the equation would appear to have all real numbers as its domain, because you're finding the inverse of this, that domain follows you. That range follows you. And then the range is 3 to infinity. Now, with that in mind, what does this picture look like?
Just the right side.
Just the right side. That's your inverse. Just the right side. When you are using one function to find a new function, whether it's inverses or compositions, you gotta pay attention to the domain. Because it doesn't change, okay? All right. One more. P of x equals x cubed minus y. Okay,
So
what's this gonna look
with
like?
this one, can we do like what we did on the first one? Like opposite would be the cube root of x plus 5.
Yep, when I switch the variables, so I'll add 5, and then I'll cube root. You know what this looks like? What's that original look like? It's a squiggly, right? Your cubic squiggly, move down 5, which doesn't change the squiggle. It's just instead of squiggling through here, it's going to squiggle through down here like this, right? of that guy? All real numbers, right? So what's the domain and range of this gonna be? All reals. So we don't have any issues here. This is the inverse. We don't have any issues at all with it because there's no restrictions on any domain.
Now, had it been like, since it's a cube root, the negative doesn't matter, but if it's
Exactly.
a square root,
Then we're gonna have problems.
okay.
Yep.
So the inverse would only be half of that equation?
Well, the original would have been a full parabola. And so the inverse, you would have to do plus or minus. And then the domain part would have been taken care of by the original too. So, let's just look at one. So if the original was the square root of, no, that's not what you're talking about. What you're talking about, the original was x squared plus 5. Okay, which we know what that looks like. So the original is right here, right? Now, is there any domain issue with that?
No.
Is there a range issue with it? No, it's not all real. Your range is everything from 5 up, right? Now, that is gonna take care of your domain in the inverse, right? So when I find the inverse, I'll switch my ordered pairs. And then I'm gonna take the square root, but when I take the square root physically myself, when it's not part of the problem, I have to remember to do plus or minus. And then that will graph, that has a domain of x has to be bigger than or equal to 5, which we expected to happen, but it has a range of all real numbers, because when I graph that, I'm gonna have the top half of the parabola and the bottom half of the parabola,
Okay.
because of the plus or minus.
That makes sense.
Okay. Could you graph, the inverse of this wild and wacky shape here? Yes. Looks like the first ordered pair in the graph, I'm looking left to right, is negative 2, 2. So I'll plot 2, negative 2. And then I have negative 1, which isn't going to change. And then I have 0, 1. And 2, 0. And 3, 1. There's my inverse.
So in those where we just have, is there any algebra?
Nope.
Nope. Just have to
Just
plot.
flip the ordered pairs, yep. Everybody okay with that? All right, now we're going to actually verify or prove that a couple of things are inverses. Besides doing the problem and finding the inverse yourself, can anybody think of a way to actually prove that these two guys are inverses? Well, I actually wrote it out for you. If things are inverses, they undo each other. So that means, in specific examples, if these are inverses, if I plug a 5 into F, it would give me a 2. And then if I put the 2 into G, it gives me back my 5. Now, that has to be true for every value of the variable. So in other words, if I put x in, I get x plus 3 over 4, whatever that is. And then if I put x plus 3 over 4 in, I have to get my x back again. That's your proof right there. If you find g of x plus 3 over 4, you have to get x. Do you? When you do this math, Do you get X?
The fours cancels your
The
three
fours
cancel.
cancel. X plus 3 minus 3 is X. But here's the kicker, it has to work the other direction too. So in other words, if you start with G and then plug that into F, it also has to equal X. So that would look like, I just did G of F. That's the one we just did. We started with F and plugged it into G. Now I gotta go the other way. So G is 4x minus 3. Oops, G is 4x minus 3. And if I plug that into F, I better get X again. Do I?
Yeah.
Does that equal X? That's your proof. So how do you prove that things are inverses? You build the composition F of G and G of F and prove that they both equal whatever you started with. Try B. Do the same thing with letter B. Huh? I think they're inverses, but they might not be. You have to plug one into the other. You have to do both, so it doesn't really matter what you start with. So if I plug G into F. That's kind of a mess. Maybe we better talk about this for a second. I started, you could do it either way. I started by putting G into F. Okay, so does that look okay? Now, to clean that up, you can do it however you're comfortable. It doesn't matter. What I always do is I multiply everything by the common denominator. Because that will remove these fractions, which are causing all the trouble. And I'll be left with 1 plus x minus 1 over 1, which is x, which is exactly what I needed to have happen. I started with an x, I gotta end with an x. Now again, you can clean that up however you want. You gotta clean it up, obviously. You can do it however you want. This works out easiest for me. You're not done though, because honestly, it's possible for it to work one direction and not the other. It's rare, but it is possible. There are things called right inverses and left inverses. So we want to make sure that it works both ways. So now I'm going to plug F into G. I'll multiply everything by X. Again, you don't have to do whatever you want with it, but I'm going to multiply everything by X. Cancel that out. So X over X plus 1 minus X. Got it. Anybody have a question about that? Yeah,
I mean, I don't exactly have a question about this, but I was looking at the homework.
Uh-huh.
Before it says prove that F and G are inverses by showing basically what we're doing, but it's just giving you equations, what would we?
Oh, I think that's the one you emailed us about.
Send an email about that?
Oh.
Yeah,
Um,
very bad, because you're not supposed to be doing homework right now, you're supposed to be paying
no.
attention.
I wasn't.
Okay, all right, make sure you're
I-
paying attention. Okay. All right, now we're ready for number 7, then we'll have 1.5 finished. So here we go, number 7. The formula for converting Celsius to Kelvin is this.
Oh, we can just make it.
The formula for converting Fahrenheit to Celsius is this. Find a formula for this, all right. So some of you have seen these formulas before, according to Sir. Okay, X equals the Fahrenheit temperature. Okay. A says find a formula for C inverse. Well, that's easy enough, isn't it?
So then it would be,
This tells us, let's see if we can do this in our heads. This tells us that we take a temperature and we subtract 32, and then we multiply by 5/9. So if we went backwards, we would multiply by 9/5 and then add 32. So intuitively, I'm thinking this is the answer. But if you don't trust that or you're a little bit leery of it, why don't we go ahead and figure it out? So we're gonna find the inverse of this equation. So X equals 5/9, Y minus 32. Can we do 9/5 X equals Y minus 32, and Y equals 9/5 X plus 32? So that's the inverse. Now, if the original changed Fahrenheit into Celsius, what does the inverse do? Change Celsius into Fahrenheit? So you probably have seen that formula too. Now, find the composition K of C. You right?
Like on that, it said it had both of them in parentheses, and it had the x minus 32 in parentheses. So wouldn't that distribute the 5/9 distribute?
You could, but if you did that, okay, so you'd have 5/9 X minus
that's so great.
160 over 9,
Mm-hmm.
is that right?
But it wouldn't be like 9/5 x plus 32. It would be the distribute, like you would still have to distribute the 9/5. Right?
Okay, this is the original function, right?
Mm-hmm.
So I'm gonna find the inverse of this. Okay, I've distributed it, now I'm gonna find the inverse. And I'm gonna see if this is what I end up with. Okay, so if I switch my variables here, I'm gonna add that 169 over here. And now I'm gonna multiply by 9, I'll do it that one, 9x plus 160 equals 5. And divide by 5. So I'm gonna get 9/5 x plus 32. Same thing. All right, so back to this, we're finding this composition. Anybody have that done? What's that look like?
Do C of X, and then plug C of X into K.
Yep, I'm gonna plug C into K. So C into K would be 5/9 x minus 32 plus 273.16. is 596 minus, what did I say that was, 169? Alright, I should be able to get a decimal for that. I got 255, which is positive, 255.382. What you got? So what does that do? Now remember, C took Fahrenheit and changed it into Celsius.
That takes Celsius and turns
So
it to
this then took Celsius and changed it into
Kelvin.
Kelvin. So the whole thing altogether does what?
Fahrenheit.
Fahrenheit to Kelvin, right, without that middle step. What's the significance of that number right there? I don't know, I'm not.
There is no significance,
There
it's just a
isn't?
number they chose, yeah.
Okay. All right, so 1.5 is gonna be due on Thursday. So, and I'm not quite clear on the schedule for tomorrow. You guys know you have all your classes
It's
tomorrow,
all
right?
classes tomorrow for 30
Including
minutes.
this one, but they're not very
There's
long.
like
We have
different-
other activities to do. So bring your stuff, but we may end up doing no math tomorrow.
Cringe,
Which right now is a thought.
I like,
But bring your stuff just in case we have time. All right, 1.6, we have already talked about the bulk of this. There are a few transformations we haven't discussed yet, particularly absolute value. But let's, first of all, get some vocabulary under control. When we start changing these shapes, doing different things to these shapes, we can translate them, reflect them, or rotate them. Translate is when you pick it up and put it down somewhere else. Translations, you can see a translation in your problem because it involves an addition or a subtraction. Okay? An addition or, I left one off. We're gonna talk about something else. But if you add or subtract, so if you took your, your squaring function, and you added 2 to the x, that would preserve the exact shape of x squared, but it would move it 2 units to the left, right? Same thing if you put a number on the end. That preserves the shape of it, does not change the shape of it at all, just puts it down in different places, like cutting and pasting. That's called a translation. A reflection is when you take the picture and reflect it across something. Reflections across the axes, so reflection across the x-axis and the y-axis are accomplished by negative signs. So if we take again our regular squaring function and we put a negative outside the x squared, what does that do? When you put the negative on the function itself, that reflects you across the x-axis. So that parabola would be upside down. You're all familiar with that. There's nothing new, don't make it complicated.
Can you say what the translation one was again?
Picks it up, moves it sideways, or up and down. Cut it out, paste it, put it down somewhere else. Now, if the x, so if the x is on the whole function, like right here, then the reflection is across the x-axis. If the negative is on the whole function, your reflection's across the x-axis. If your negative is on the x, just the x, then the reflection is across the y-axis. Now, what happens with this particular curve if we put a negative on the x? Nothing. So it is what's called an even function, right? It is symmetric about the y-axis. this reflects across y. For this function, it doesn't change anything.
How would we like visualize that? If we were gonna see like a normal function, like, would that be like y equals parentheses negative x
Mhm. Yep,
squared?
yep.
Okay. And then like if there
Just
were
like it looks like right here, yep. So this would be f of negative x would be negative x squared.
if it was like horizontal translations, it would just be negative x plus 2, say,
Yep.
in and then squared. Okay.
Yep.
But if it
So,
was out,
right now, what we need to remember is, when you put a negative on the function itself, that is across x. When you put it on just the x, it is across y. That mimics your test of symmetry. Remember, when you change the sign on y, you reflect across the x-axis. When you change the sign on x, you reflect across the y-axis. So those reflections are exactly the same as your symmetry test that we talked about a few days ago. And then we have rotations. We are not going to spend any time really with rotations right now. Hopefully we will get to that when we get to our matrix chapter, because we can do rotations then. But a rotation, very common one is to take an ellipse, let's say, and rotate it. So instead of being situated horizontally, it's now situated on the diagonal. We are not going to spend time with those right now, but that is a kind of transformation. And then a big one that I left off, and I have no idea why I left it off, are the stretches and the shrinks. Because we can take our shapes and stretch and shrink them. So that happens when we put, let's say here's our function. If we put a coefficient or a multiplier into the problem, you're going to stretch it or shrink it one way or the other. If you put a coefficient in front of the whole function, if you apply it to the whole function, this is a vertical stretch or shrink. And it's a stretch if it's bigger than 1, and it's a shrink if it's less than 1. So in other words, this would take whatever picture you have and make it half as tall. It shrinks it if the coefficient's less than 1. So if the number, the coefficient, the multiplier, is on the whole function, not the x, the whole function, then you're going to stretch it or shrink it vertically. So make it taller, make it shorter, depending on the size of the number.
So it'll be something like y equals 1/2 parentheses x plus 2.
Yeah.
Okay.
Now, if the coefficient, whatever it happens to be, I'm using 1/2, but it could be 2 or 5 or 7, anything. If the coefficient is on the x, that's a horizontal stretch or shrink. That's going to change you this way. If the number is bigger, or excuse me, if the number is less than 1, it's a stretch. So believe it or not, that picture is going to be twice as long as the original. So whatever your original picture was, this would stretch it out twice as long. If the number is bigger than 1, it's a shrink. So if you had this, that would actually be half as wide as the original. So whatever the original picture looked like, this one will be half that wide. So if the original, let's say the original looked like this, if that was the original, then this one would look like this. Half as wide. Okay? So now what we're gonna do is start applying all of this stuff to some of our pictures. Probably have to do absolute value next time. Let's see how far we can get with these pictures. Consider your squaring function, y equals x squared. What's that first one look like? Same parabola as the original, but now position 1 unit to the left. So let's get in the habit of labeling these points. What about B? What's B gonna look like? Up 1. And what's C gonna look like? Upside down, reflected. That's called a reflection. It's reflected across the x-axis. It's simply upside down. Easy. Now let's do the same thing with our ln function, our natural logarithm function. You might want to keep in mind what that one looks like. That's what it looks like, right? That's our BFF, which we've memorized. Now, what would the upside down of it be? That picture reflected across the x-axis. Is it going to change the asymptote?
No.
Nope. Is it going to change the zero?
No.
Nope. But instead of starting down and going up, it's going to start up and go down. What about this one?
One to the right, which means that 0 is going to be at 0, 2.
2,0.
Sorry, 2,
And the asymptote is going to be at x equals 1. Watch this one now, be careful. What does changing the sign on x do? This way, right? So take my original picture and fold it over here. So that actually won't change the asymptote, right? But now my 0 will be at -1, 0. And I'm folding it over, so isn't it gonna look like this? We'll do this problem and then I'll be done for the day, okay? So here we go. No BFF, just some kind of weird shape. And we are going to do some absolute value transformations on it. So these are kind of separate, they're not like part of the normal. And let me graph the original. Here's the original. Now, certainly, we could move that left and right, up and down, stretch it, shrink it, whatever. But that's not what we're doing here. We're taking the absolute value of it. Think about that for a minute. What happens when you take the absolute value of something? It becomes positive, right? So doesn't this say that all of your y's will now have to be positive? So whatever the y's are, they have to be positive. Well, let's look right here at this little trapezoid. Are those y's already positive? Okay, so I'm just going to go ahead and redraw that guy. my trapezoid, his y's were already positive, so he doesn't change. But now what about this little triangle right here? His y's are negative, so they're gonna become the same number but positive. So aren't I just like taking just the triangle and like flipping it up? Okay, so that looks like that. What about our trapezoid over here? Same thing? So there's a picture of the absolute value of the function. Taking the absolute value of the function does nothing except change all the negative y's into positives. Sometimes we call this the bottoms up function. Because doesn't it take what's on the bottom and bring it up? That's what absolute value of the whole function does. All right, everybody on board? Okay, look at the next one. This is the last one I'm going to do. Look at the next one. It is different because it isn't the absolute value of the whole thing. It's just the absolute value of x. Now I want you to think about this for a second. The absolute value of x. If I put a 1 in there, wouldn't the answer to the question, whatever it equals, be the same as if I put a negative 1 in there? So in other words, the outputs for the positive x's must be exactly the same as the outputs for the negative x's. Would you agree with that? All right, let's look at the positive x's first, because when you do absolute value of positives, nothing changes. So here are the positive x's. Would you agree? So that part of the graph isn't changing. So whatever the positive x's look like, they're not changing. But you just told me that whatever I get when I put in positive 1 is going to be the same as when I put in negative 1. And when I put in 2, it's the same as negative 2, and so on. So I see you're up here going like this, Bronson. Because what's going to happen is, whatever you have on this side is going to have to be duplicated over here. Because you told me that the sign on that doesn't matter. So I'm going to take that exact picture and I'm going to draw it over here. There it is. When you do the absolute value of x, the right side of the picture doesn't change, and then the left side of the picture is an image of the right side. So what happened to all of this? Gone. Gone. Not there anymore, because it got replaced by these values right here. When you put in negative 1, you have to get 1. When you put in negative 2, you have to get 0, and so on and so on and so on. So when we graph the absolute value of just x, the right side of the picture stays the same, and the left side of the picture becomes the right side. So the right side translates over to the left side. Okay. Whew, lots of math. All right, so we got some homework coming due.